In this video, we're going to continue our precalculus review by introducing the idea of polynomials and then how to work with them and factor them in particular. So much of what we will be working with in this course are polynomials. So let's see what that looks like. You've all encountered these before, I'm sure, in your previous courses, whatever they may be. A polynomial is a finite sum of terms in which all the powers of the variable have only positive integer valued exponents. So the general form for a polynomial with degree n, so I'm going to talk about that in a minute, looks like a to the n, x to the n, plus a to the n minus 1, x to the n minus 1, and you continue until you get to a2 x squared plus a1 x plus a0. Okay, so that's the general form for the polynomial. So here x is the variable, and the a's, I'm going to call them ai. Okay, so all the a's are constants, so they're just numbers. And we usually call them coefficients. And n is a non-negative integer. So this has degree n because x to the n is the biggest power. So you see it's n and then things that are less than n. So that's why it's degree n. Now, some special coefficients here. The coefficient in front of the biggest power of x is called the leading coefficient. Stop there. And the one at the back is called the constant coefficient because there's no variable there. So those are just a few special ones. Now, when we're working with polynomials, we have to be cautious because we can only combine terms that have the same exponent of the variable. So we call these like terms. Okay, you've probably heard that before. So we usually say combine like terms. We want all the like terms to be together. So when you multiply polynomials, we need to use the distributive property so that it happens even when you're just multiplying by numbers. So this 2 has to go into everything in the brackets, and so does the negative here. So here we're subtracting a polynomial from another polynomial. So you have to subtract the entire second polynomial. So if I just expand these two brackets out, I have 2x to the 5th minus 2x to the 4th plus, 10 x squared, and then the minus goes through, so that's minus x to the 4 plus 3x cubed minus 4x plus 3. So now we want to just look for like terms, and there's not that many here. So I see this 2x to the 4, or negative 2x to the 4, and another negative x to the 4, but everything else has different powers of x. So those are the only like terms. So we're going to have 2x to the 5th. Now if I put those together, I have minus 2x to the 4th, and then I want to minus another one. So I'm going to have minus 3x to the 4th plus 3x cubed plus 10x squared minus 4x plus 3. Okay, so we can't simplify that anymore. If you have two polynomials that are multiplied together and they have more than one term each, then we're going to use a process you've heard of, I'm sure, called FOIL. Okay, so you take the first ones and multiply them, and then you take the outer ones and multiply them, and then the inner ones, and then the last ones. So when we do that, 3x times 2x squared, so you can times the numbers, so I get 6, and then x times x to the power 2, you want to add the exponents because they're the same base. So this is going to be x to the 3. And then we do the outer ones, we're going to have minus 12x. The inner ones is plus 4x squared, and the last ones is going to be minus 8. And we see here there's no like terms, so we can just leave it like that. The reverse of this process is what we call factoring. So the first type of factoring is when you look for a greatest common factor. You usually want to do this before you try other things of factoring. So if all the terms have something in common, you can pull that out to the front. So let's look at these two examples here. So what do these three terms all have in common? Okay, well, it looks like 4. The number 4 divides all the numbers, and then we take out the smallest power of x that's in all of them. So that's going to be x squared. And now we want to say, okay, what's left from this term? We took out 4, so there's going to be a 2 left over from the 8, and we took out 2 x's, so there's going to be 3 more x's remaining. Now in the second term, we took out the 4, so that's gone, and we took out 2 of these 3 x's, so I'm just going to have minus x here. And the last one, I took out a 4, so that leaves me with a 6 left over, and I took out all the x's. So it's just going to be 4x squared times 2x cubed minus x plus 6. Okay, this next one is a bit complicated because the factors here, it's tempting to expand this all out. That would be a mistake. Okay, now why is because you can see 2x minus 1 appears twice, as does x plus 3. Okay, so this expression just has 2 terms. Okay, because everything within those terms is multiplying. So what we want to do is factor out the things that are in common. Now, I'm just going to write at the bottom here. You could imagine this is like, I'm going to call it y is 2x minus 1 and z is x plus 3. So what this would look like is y squared, z squared, minus 2y cubed z. Okay, now this might be easier to factor. So you can take out y squared and 1z, and then we're going to have left over z minus 2y. Okay, so that is pretty simple to factor because the things you're pulling out aren't complicated. So here, the things we're going to be pulling out are complicated, but we're actually doing the exact same thing as we did in the blue. So I'm going to take out the green, the 2x minus 1, to the smaller power. Okay, so I see it to a power 2, and I see it to a power 3. So I take out 2 of them. And then I also take out these x plus 3's. So there's a 2 power here, and then there's no power here, so that's a 1. So that's smaller. So I just take out 1 of those. Okay, I'm going to do square brackets because we're pulling out something complicated. So now what's left over from the first term? We took out both of those. So there's 1 more of these x plus 3's left over. Okay, in the second term, I have the minus 2 and 1 more 2x minus 1. So minus 2, 2x minus 1. So now we just want to simplify inside that square bracket. So 2x minus 1 squared times x plus 3. And then I'm going to have x plus 3 minus 4x plus 2. So here we have some like terms. Okay, so the x and the 4x, and then the numbers. So this is 2x minus 1 squared, x plus 3, times x minus 4x is minus 3x, and 3 plus 2 is plus 5. So this is our expression in factored form. Okay, so because those 2 terms had common factors. So sometimes the polynomial will not have any common factors. Okay, there's still other ways we can factor, especially if the polynomial is a quadratic. So that means it's degree 2. So if your polynomial is of the form x squared plus bx plus c, so where b and c are integers, notice that here the leading coefficient. Okay, so the coefficient in front of the highest power of x is equal to 1. Okay, so that's important because when it's not 1, we have to do something slightly different. So when it is 1 and we have a quadratic, what we're going to do is look for two integers, m and n, that we multiply to give the c term, and we add to give the b term. If m and n are such integers, then the polynomial, so x squared plus bx plus c, is going to factor as x plus m times x plus n. Okay, so let's just see why. Okay, so if we FOIL this out, we're going to get x squared plus n x's plus m x's plus m times n. So we have some like terms here. So this is x squared plus n plus m times x's plus m n. Okay, so now we can see that this has to be equal to our b, which it was because we found such m and n, and this term has to be equal to our c, which again it also is. So let's factor the following polynomial. So notice that there's no common factor, so these terms don't have anything in common. We have a 1 leading coefficient, so we can use the method we just described. So we want two integers with m plus n equals -5, m times n equals -6. So it sometimes helps to write what multiplies to give 6. Okay, so that's going to be 1 and 6, or 2 and 3. Now we want to have a difference of 5. Okay, so that's going to be this pair here. Okay, now we want, because it multiplies to a negative, one of these has to be negative, and because we want -5 when we add them, it has to be the -6. Okay, so those are our two integers. So m is -6 and n is 1, or vice versa. So x squared minus 5x minus 6 is going to be x plus -6 times x plus 1, which we could rewrite as x minus 6 times x plus 1. So that would be in factored form. If you want to check that it works, just expand it out. So what if we have a leading coefficient that's not 1? So in other words, we have a polynomial of the form here, ax squared plus bx plus c. Then we need two integers that multiply to give a times c, but still add to give b. Okay, so when I took math ages ago, my teacher called this over the hill, because you have to take this leading coefficient and multiply it to the constant coefficient. Now, the procedure to get the factored form is a bit longer here. So we want to find two integers. So once we find these two integers, then what we're going to do is replace the term bx with two terms, mx plus nx, okay, which is the same as m plus nx, and our two numbers add to give b. So we haven't actually changed anything, okay, we just rewritten it. And then we're going to use a method called factor by grouping. So I'll just go through that in this example. Okay, so here we want to multiply to 9 times -2, so -18, and add to -3. So what multiplies to give 18? So 1 and 18, 2 and 9, 3 and 6, and that's it. And we want to add them to -3, so one of them is going to be negative, so I want them to have a difference of 3. So the only ones that do are the 3 and the 6, and we're going to need the 6 to be negative. So those are our two integers. So now we take this quadratic, we keep the first term the same, But now instead of the minus 3x, I'm going to write it as minus 6x plus 3x minus 2. Okay, so notice, maybe I'll do it in this, that these two together equal that term if we put them together because they're like terms. So we haven't changed anything. Now what the factor by grouping does is it just splits this into 2 bits. And then we look for common factors in each bit. So in this first pair, what's common to 9x squared minus 6x? So we can take out a 3 and an x, and we'll be left with 3x minus 2. Okay, now these two don't have, the next two don't have anything in common, but you can always pull out a 1 or a minus 1. So then we get that. So the goal when we're doing this, so if we've done it correctly, these two things left over should be the same. So the benefit of this is now we can pull that term, that term out from each. So I take out the 3x minus 2, and in the first term here, I'm left with only this 3x. Okay, and in the second term here, I have this plus 1. So now I have it in factored form. When you can't find such integers, you can still factor the polynomial sometimes using some special factorizations, or if you, as a last resort, the quadratic formula. This will find factors that are non-integers, so that's handy. So I've written it 2 different ways here. So the polynomial of the form ax squared plus bx plus c can be factored as x minus m, x minus n, where m is negative b plus the square root of b squared minus 4ac all over 2a, and n is negative b minus the same square root all over 2a. So notice they're exactly the same except for the addition symbol in between. Now more the way we normally see the quadratic formula is when you want to solve a quadratic. So if you want to solve this equation where it equals 0, then your x is going to be, so x value equals negative b plus or minus, so you get the 2 values all at once, b squared minus 4ac all over 2a. Okay, so that's probably how you recognize it from before. Some special factorizations that I've talked about already a bit. So x squared minus y squared, this is a difference of squares. So we actually used this already when we did rationalizing. So this factors as x plus y times x minus y. So you multiply the conjugates together. So this is a difference of squares. Okay, this one is very important. We use this one a lot. And then we have a perfect square. So you can factor as x plus y all squared if you have x plus y times x plus y. And if you expand that out, you get x squared plus 2xy plus y squared. So that's what a perfect square looks like. And then we have the difference of cubes, which factors as x minus y times x squared plus xy plus y squared. So that's the difference of cubes. And then we have the sum of cubes, which does factor even though the sum of squares doesn't. So x plus y times x squared minus xy plus y squared. So these two are very similar. So those are some special ones. I highly recommend that you know the difference of squares, and it's useful to know what a perfect square looks like as well. The cube ones I wouldn't expect you to memorize, but it is useful to know them as well. So that's a brief factoring.